Welcome to Operator SDK Office Hours. My name is Eric Straczynski, and I'm a senior software engineer on the Operator SDK team at Red Hat. Operator SDK is part of the Operator Framework, a CNCF incubating project containing software for managing operator development and deployment. Today I'll be discussing operator packaging and deployment in the context of Operator Framework concepts and tools. Let's start off by answering the question, what is an operator? An operator is a Kubernetes API extension in the form of controllers that automate application workflows in a cluster setting. These controllers are responsible for managing developer-defined APIs that map to application concepts called custom resource definitions. Instantiations of these definitions, called custom resources, can be interacted with by users and automated processes. When a user or automated process modifies a custom resource, the controller reconciles the modification event to ensure the custom resource eventually adopts a desired state. So how do you actually build one of these operators? Well, with the Operator SDK. The Operator SDK project contains tools that promote best practices for operator development. The project centers around the Operator SDK tool, which scaffolds, enables testing of, and packages operator projects. An operator project can be packaged into an object called a bundle, which is an image containing a set of metadata and manifests for an operator at a particular release or version. Operator metadata defines the operator at a package level and consists of elements like package name, API dependencies, and UI metadata for various cluster consoles. Operator manifests define the functionality of your operator declaratively and consists of manifests like deployments, roles and cluster roles, and custom resource definitions, also known as CRDs. A set of bundles for the same package name can be combined with other sets into a catalog. The catalog is an image object containing information about available operators, their deployment information and update graphs, and allows for in-cluster discoverability. These operator catalogs can be consumed by the Operator Lifecycle Manager, or OLM. As the name implies, OLM manages the entire lifecycle of your operator, from API dependency resolution to installation to updates. Your operator's bundles inform OLM how to install and update safely through their constituent manifests and metadata. Now I'll go through a two-part demo that steps through building and packaging an operator. The first part involves creating a Go operator project and creating and testing a single operator bundle. The second part involves creating and running a catalog for this operator. I won't go into depth discussing Go operator projects, as there is already another demo doing so, but I will discuss OLM-specific components of the project. The first part of this demo requires a few prerequisites: an internet connection for downloading images and a few dependencies, Operator SDK and kubectl binaries, and access to a Kubernetes cluster of version 1.16 or above with the default service account configured with cluster admin permissions. We'll be using Kind to create a Kubernetes cluster in this demo. Now that we have all of our prerequisite tools installed, we can get started by creating a Go operator project for the Memcache software. Memcached is a distributed memory object caching system that can replicate objects across multiple nodes. The operator will contain a single API, a controller for that API, and validating and mutating webhooks that validate and default Memcache custom resources. So let's first create a demo directory and head into that demo directory. So first, we'll initialize our project. Project name is Memcached operator. So now that we have our API, or now that we have our project, we can create some APIs for it. Like I said, we'll be creating one API, group cache version v1 alpha 1 kind memcached, and we'll be creating API types and a controller for our API. Next, we'll create some webhooks. For this API, we'll be creating defaulting and programmatic validation webhooks. So that's mutating and validation webhooks. I've already implemented the types and webhooks, which I'll copy into the project. We can take a look at them as well. So here I've added size to our spec and pod statuses to our status. You can ignore these comments for now. I'll get to them in a little bit. The status is using the operator lib status package. Right. And I've also implemented the controller. Which we can take a look at right now. It's a pretty straightforward controller. All it does is inspect the custom resources and deployment and make sure that replicas are matching the size of the spec. Yeah, pretty straightforward. Definitely not production software, but informative for this demo. We'll also copy in some samples, which I'll get to in a little bit. And we also need to set up customization for our project. If you've already watched or plan to watch the Go operator demo or any of the operator type demos, they will thoroughly explain what is in the config directory. Here I've uncommented the webhooks and Prometheus bases so that our webhooks and Prometheus metrics setup will be added to our operator manifests. That's all we need to do here. There's quite a bit more to do down here if you were going to do a vanilla Kubernetes deployment without OLM, but we don't need to do that because OLM will manage most of this for us. Just going to install the operator lib version that we need. And now we can build our operator image. So I've already built and pushed this image, and I believe there are some weird errors that come up right now. So we'll ignore that for now. It already exists remotely, so we can just use that going forward. And now we can actually build the bundle. So what this is doing is it's running a few different operator SDK commands. One of which is generating some customized manifests for us. And these manifests require some UI metadata. So let's enter that now. So the operator display name, description, provider, that's me, some URL for our operator or the underlying software, uncached, and maintainers. Great. So as you can see, it ran a couple different commands, most of which are just scaffolding out what I'll show you in a minute, which is our bundle directory. And I'd also like to point out that the operator SDK bundle validate command was also run to make sure that the bundle is statically valid. So now let's take a look at what we just built. Now we have this bundle directory that contains the manifests, metadata, and some scorecard stuff, which I won't be getting into in this tutorial. The manifests and metadata were what I was discussing before. We can first take a look at our most important manifest, the cluster service version. The cluster service version is a compilation of the functional parts of our operator into one deployable file that OLM will manage. Here we can see that there is an example of a custom resource. We have our custom resource definitions listed here, some UI metadata, our cluster permissions. This is just RBAC that's been compiled into one list. Here's our manager deployments. And down here we have some more metadata and now our webhook definitions. We can see that the version is currently on 0.0.1. Great. Everything else in manifests, like our CRD and some extra stuff, is they're all things that OLM doesn't directly manage through the CSV, but they will directly, OLM will directly apply these in the namespace of your choosing for your operator to use. Let's also take a look at the manifests. Or sorry, the metadata, excuse me. So here we have a bunch of annotations that define what is in our bundle image. Here we have a channel. This is the default channel scaffolded by the SDK. That operator versions that we specify under this channel will go into and can be installed by OLM. Here's our package name, and here are some other things that are used by the SDK. And there's also a bundled Docker file scaffold that contains the same metadata that I just showed you, and then some copy directives to move all of our manifest metadata into the resulting bundle image. That'll be useful when we actually build the bundle image. But first, I would like to add a few things to our CSV. First of all, we can actually add some descriptors to our CSV for the spec and status. So these two comments will tell the SDK's generator to add X descriptors for both the spec and the status, pod count and pod statuses, for the size and pod statuses field, respectively. And then I've also implemented a webhook patch to add a webhook port to our manager deployment. Okay, so now let's take a look at what I just added. So first of all, I've added this patch file to our customization.yaml, which will add this OLM Manager webhook patch that I've created, which will patch our manager's deployment to add port 9443, which exposes our webhooks. And we can take a look at the actual patch itself. So I basically copied this from the existing default webhook manager patch, but removed the volumes and volume mounts. So this just contains the webhook port. Great, now that's all set up, we can regenerate the bundle. And we'll take a look at our cluster service version again. Right. So, as you can see, we've added these spec and status descriptors containing these X descriptors using those marker comments. And for each of those fields, we've also added some extra console UI information. And then we take a look at our manager, and we can see that this webhook port has been added. Great. So now our bundle is fully configured, and we can actually build the bundle image. So this is just using the bundle.docker file to create our bundle image. The bundle image contains the manifest and metadata, like I said before, and has these annotations applied as labels. Great. And now we should probably push our bundle image. Okay, so now that that's done, we can get around to actually running the bundle image using operator SDK run bundle. So now we have to do a few things. We actually have to install Prometheus from Metrics. And because we're using kind, we want to load our operator image into the cluster. Next, we can actually install OLM itself into the cluster with operator SDK OLM install. This command will pull manifests from GitHub and install OLM through those manifests. These are using manifests from OLM's releases page in GitHub. So you can go through and do this yourself, but OLM install will manage this for you and print out some nice logs as well. So as you can see here, there are a couple of APIs listed for OLM that you don't actually need to worry too much about in this tutorial, because the tooling here will handle creating these for you. This takes a few seconds to get installed. Great, everything's installed and running. So now we can run our bundle. So those APIs that I mentioned before, run bundle will actually handle creating those for you in the correct order. And what this will do is actually create an ephemeral catalog that will serve your operator's bundle to OLM. And OLM will detect that catalog exists and pull the manifest from it and install them as you've specified. Great. And as you can see, run bundle will actually step through all of the status phases that occur on the cluster service version and inform you when everything has succeeded. Great, so it looks like our operator has been installed, but to check that, let's look at the manager pod. Yep, so the image that is currently installed is our 001 image. That's great. Now let's try and apply some CRs, some custom resources. So this particular CR is invalid, and so the webhook that we've created should return an error when we try and apply it. Yep, the cluster size must be an odd number. That's working as expected, and now let's see if a valid but zeroed out size in our CR will work. So the defaulting or mutating webhook that we've created should default this to 5. That was created. And let's actually check the size. Yep, the size is 5. Great. So that concludes the first part of our demo. So now let's start on our the second part of our demo. So now that we've taken the first step towards a production-ready operator, let's take the next step. Before we begin, there are a few more prerequisites in addition to those in the first part. The operator package managing tool, OPM, and the kubectl operator plugin. The links to install those are in the slides. To demonstrate a typical development scenario, we first want to upgrade our operator version to 002. After we build a new bundle for this operator version, we can combine it and the previous bundle into a catalog using the OPM index add command. The kubectl operator plugin, which manages the set of OLM APIs for you, can directly add and install the latest operator version in the catalog for us. let's get started with that. All right, first, let's upgrade our operator to 002. That was easy. So now we want to build our operator image, which I've already done, so we don't have to worry about that, and that exists remotely. And now we want to build our 002 bundle, and this is using the 002 operator image. So just as before, the make bundle target will invoke a bunch of SDK commands and regenerate the bundle directory. Let's take a look at our CSV now. Here we can see that the name has been upgraded to 002. And down below here, our version has been bumped to 002. And we have this new replaces directive for 001 CSV, which tells OLM that this CSV is to replace the 001 CSV. Cool, so now we want to build our 002 bundle image. So this is more or less the same image, except that the manifest directory now contains our 002 CSV. And we also want to push this image. Awesome. And as before, we also want to load both of our 001 and 002 operator images into the cluster, because we're using a kind cluster for this demo. And I've already pre-installed OLM onto this cluster, so we don't need to worry about doing that. Now for the fun part. So now we want to call this OPM index add function, which will take our bundles 001 and 002 and add them to something called an index image, which is the underlying image object for a catalog. And we also want to call it something like memcache operator index, which we've done here. So what this command is doing is shelling out to an image tool like Podman in this instance, and building this index image using a base image. So now that we've created this index image, we can push it like any other image. And we've got our catalog. So now what we want to do is use the kubectl operator catalog add function to actually add this catalog to our cluster so that it can be served to OLM. So what this command is doing is creating a pod that uses this index image as its base image, and also creating something called a catalog source, which connects our pod to OLM and allows that pod to serve your operator versions to OLM so that we can install them later. And here we've specified the package name to this command so that we can use that in the future. Because remember, there are multiple operator versions, operator channels, what have you, in your index image, and we need to be able to specify that later, along with some sort of version information or channel information. Great, so we've created our memcache operator catalog in the cluster. And now we actually want to install the memcache operator. So here we've specified the package name, and we've also said another few things here. The channel is that alpha channel that I showed you before in the metadata. That specifies what set of operators I want to upgrade or install and then upgrade through. There's the 001 and 002 operator versions in that channel, and so I want to automatically install 001 and then upgrade to 002, which is the channel head. Then this create operator group flag creates something called an operator group in the cluster that manages operator namespacing. So here, the plugin has reported that we have installed the 002 CSV, which installs our 002 operator. To confirm this, let's take a look at what image is in our manager pod. Yep, it looks like memcache operator 002 is being used. So let's try out some of these samples again. So yep, it looks like the webhook is running because it's rejected this invalid custom resource. And let's take another look at applying a valid custom resource. Yep, that's been created. So to summarize, OLM has installed our operator at version 002, which is the alpha channel head. Even though 001 is available, it knows that there is a newer version that you should install too. Great. So that concludes the demo. Here are some links to relevant pieces of software, such as the SDK OLM integration documentation, the operator SDK project itself, and the repo containing the project used in this demo, complete with instructions. Thank you so much for attending, and have a great KubeCon.